Today we are talking about the critical review of the evaluation of various relationships of reaeration rate coefficients for modeling dissolved oxygen in a river with extreme flow variations in Pakistan. The abstract basically talked about a mathematical relationship developed to theorize reaeration rate coefficients in the River Ravi in Pakistan. Relations contain several variables such as depth, velocity, width, and slope. And from that, 29 relationships were divided into 4 groups based on different characteristics and the variables used. The evaluation of the relations was based on the correlation between the values from the available equations and the measured DO concentrations in the samples from the river. The results then identified the important parameters affecting aeration rate as well as Ka suitability.
So, oxygen gets into the river due to atmospheric aeration from the contact of the atmosphere to the surface of the river. And that's run by Henry's law. And then whenever wastewater is dumped into the river, the dissolved oxygen is decreased due to BOD and COD and other things like that. And this may use up all of the dissolved oxygen. So like I said, surface contact with air constantly adds water back into the surface contact. So like I said earlier, surface contact with air constantly adds oxygen back into the water. So the reaeration is the major source of dissolved oxygen, and it's modeled by the mass transfer of oxygen, which is from this equation, where C is the concentration of oxygen, T is time, and Ka is the reaeration coefficient. Countries like Pakistan, they have high amounts of untreated wastewater, and whenever the flow is low, there's not very much oxygen being reaerated into the rivers. So their low flow rivers have very close to zero dissolved oxygen levels. So they want to avoid this, but the problem is the dissolved oxygen cannot be monitored during low flow and anaerobic conditions. And the DO-SAG model, more particularly the Ka in the model, can only be used in medium flow conditions, and we want to know how the dissolved oxygen behaves during low flow conditions. So we want to formulate a Ka value that can accommodate abrupt hydraulic variations in rivers near cities with these low flows. So the goal is to compare the dissolved oxygen model results with the actual dissolved oxygen levels under low and medium flow conditions. And then we can look at those results and sort of see where we can apply the reaeration coefficient whenever they change in the flow rate.
Okay, so the theory and classifications of these reaeration relationships starts with the mass transfer rate of oxygen. That was the equation that was in the introduction. Then it moves to the flux of oxygen through the liquid film, and that is just the rate of change of dissolved oxygen in a volume per unit area. So then equation 3 is pretty much equation 2 rewritten. Equation 4 is a comparison between 2 and 3. Then 5 explains the Kl value. Then number 6 explains the most important, the Ka value. And I go back. So in the Ka value, there's this dl, a delta, and a capital H. The dl is diffusion coefficient, which includes molecular and turbulent diffusion. H is the mean stream depth, and delta is the thickness of the liquid film. Equation 7 refers to the group 1 equations where river velocity and river depth are the only things in the function. Equation 8 refers to group 2 where the slope of the stream is included. Group 3 refers to equation 9 where shear velocity and a Froude number is included. Then group 4 includes a bunch of different more variables. dm is a molecular diffusion coefficient, g is the acceleration due to gravity, b is kinematic viscosity, and the RGT value is a gas transfer Reynolds number. Then this 11th equation is a correction equation for temperature, the Ka value.
Okay, so as far as the methodology goes, the study reached a 100-kilometer portion of the River Ravi, and the wastewater flow on average was 40 meters cubed per second. And the river flow, as Jay said, it varied a lot, and so it was between 10 meters cubed per second and 10,000 meters cubed per second. The two data sets that they ended up using in their analysis was one that was encompassing when the river was at a medium flow of 431.15 meters cubed per second, and the other data set was at low flow and was 52.6 meters cubed per second. And then in their analysis, they essentially used equations that were discussed in the theory portion to estimate the Ka using hydrodynamic models.
So in general, it was found that 10 of the 29 equations that were studied were found to be applicable for modeling low and medium flow radiation constants for the rivers. Of these 13 equations, the O'Connor, Dobbins, Van Zyl, Churchill, Langenbean and Durham, Isaacs and Gowdy, Padium and Gulia were all top performers when you're looking at the SSR and R squared values. And all of these equations were found to be in group 1. Of the 13 equations in group 1, 9 of the equations were applicable in modeling Ka values for low and medium flow. The Batchelor and Lazo was not found applicable for either, and the Elobaldi and Isaac were found inclusive for low flow modeling, while the Neglusko and Rojansky was found not suitable for medium flow modeling in the rivers. The group 2 equations appear to work best for low flow conditions and not suitable for medium flow, except for the Tyskelovli and Neal, which was found the opposite, so it worked better for your medium flow than it did for your low flow. In group 3, only one of the equations, the lab, was found suitable for modeling radiation constants in the low flow conditions, while the others were not found applicable for modeling the Ka values for the River Ravi in Pakistan. The only equation that was in group 4 was found to be suitable for both low flow and medium flow modeling of the river.
Okay, so overall for group 1, it is suggested that the depth and velocity are the most important for factors in estimating the reaeration constant in the Ravi River. For group 4, the equation had good predictability when the parameters of flow, depth, and velocity were considered. Considering other parameters such as molecular diffusion coefficient, acceleration due to gravity, kinetic viscosity, and the gas transfer Reynolds number only improved its capabilities of predicting the Ka.
So the first critique that we had was that the temperature correction for the Ka values was mentioned later in the theory section, but it does not attempt to explain the theta value, which they sort of say that the average value that is used is 1.024, and they didn't really explain how they came to that. So
The second critique was with regards to the sampling sets. As before stated, the sampling sets chosen covered only medium and low flow, and it was discussed in the introduction that that the model can only really be used for medium and low flow because it's not as applicable to high flow. But in the methodology section, they state that the river goes up to a flow of 10,000 meters cubed per second, and then they don't discuss why they didn't incorporate that in. So I think it would have been helpful for them to re-reference the fact that their model that they use probably wouldn't work with the high flow. So I think that was more of like a reader-based thing that it just would have been helpful for them to get their point across.
Again, for the critique number 3, for the results and discussion, the results and discussion section was not well organized as far as it keeping the equations straight. They were broke up into groups. And groups 1 and 2 had a large number of equations to keep track of. It just made it difficult to really understand and to keep flow through article. They tried to evaluate too many equations at one time also. A fix for this would be to create more groups with a smaller number of equations in each group. They could have broken up the paper into sections, just discussing each group with the data tables for that group, instead of trying to discuss the groups together in one large section.